Hello, everybody. Welcome to week 9. This is the only recording that I'm going to make for both week 9 and week 10. That's next week because you have a midterm. That means 1 hour is taken out of our schedule. And this is a very long presentation. And I have another very long presentation after this on trees and graph theory. We're running ahead of schedule. I mean, I'm going to end up uh, having to put in another section you probably won't like. It should be there on computational complexity and uh, theoretical computing science, Turing machines, and so forth. These are things you should know about, but you'll probably learn them in other um, courses. But let's just see what happens. Okay, this is a long presentation, so it's for week 9, and it'll cover next week as well, unless I have more time available afterwards. Let's just see what happens. So, so here we are. This is about relations and functions. This is chapter 9, I believe. Chapter 9. I put 8 here because I thought this is going to be week 8. Doesn't really matter. Um, So, introduction, we'll talk about relations. I'll define them for you, and a special kind of relation is a function. In fact, your book, Rosen, puts functions in chapter 3. I've mentioned this already. It's not where it should be unless you're doing this, unless you're directing the course and textbook strictly towards computing sciences majors. I think it should be more or less a math course that forms the basis of computing science. And it belongs with relations, as the other textbook, Grimaldi, puts it. I'm used to that. I like that grouping. So let's just put these together. A bit of chapter 3 on relations and a lot from chapter 9. Sorry, a bit of functions in chapter 3, not relations, and their proper setting in chapter 9 with relations. So let's just go ahead. So this is where we are right here, right now. We ended combinatorics of functions and relations, chapter 9. So then we want to go into trees and hopefully formal languages. We might have enough time for all that. According to this right here, we have, well, 1, 2, 3, 4 weeks. That'll be a review. 5 weeks left. We have plenty of time. We're well ahead of the game. Well ahead. Okay. So, we review the basics of discrete relations and functions and their various strategies. Introduce digraphs. That means directed graph. It's a special kind of graph. We will talk about graph theory after this. So you're introduced to digraphs ahead of time. And discuss the cardinality of these discrete relations. In fact, only functions. We'll only talk about the cardinality of functions. The cardinality of relations, I think, is just a little too much for this course and for this chapter. I usually omit it. It's not as important as the cardinality of functions. There's only 3 of them, really. Okay, so introduction to discrete relations. So what we have here is a relation is association or link between elements of one set called the domain, that's A, and the other set called the range. Okay, that's this part right here. Okay, F of A maps to this area right here, but this is all called the codomain B. So if you map entirely from set A to set B in a one-to-one relationship, then it's a one-to-one function, for example. But if you just map to just part of it, that's called an onto function. So I'm introducing those terms ahead of time. So the domain is all possible inputs of the function A. Codomain is all all values the function could possibly output. Okay, and the range is all values the function actually outputs. Okay, this is what it could output, the codomain, but it only outputs a subset, generally speaking, and because not every function is a one-to-one function. Okay, so relations exist between objects of the same set or between objects of 2 or more sets. As we've seen back here, F of A and B, these are 2 sets, A and B separately. In mathematics, logic, a relation is a property that assigns truth value to k tuples. So what does that mean? It means ordered pairs, ordered triplets, ordered fourlets, ordered k-lets. Okay, triplets, k-lets. Like an ordered pair is just simply Something, or ordered triple is something like this. So that's a three tuple. Generally speaking, okay, this could represent our three real space if this was x, y, and z as continuous variables. Um, or if it's just x, y, then it's a binary relation, and that would be the real plane. Okay, so specifically, what are we saying here? Beatrice Wood was introduced to Henri Pierre Rocher by Marcel Duchamp is true, while Karl Marx was introduced to Frederick Engels by Queen Victoria is false. That's something I want you to look at and think about. Okay, um, it's just simply the logic behind these relations. So let's go now get into relations. This is from your textbook. A relation is you've already been introduced to the cross product in chapter in set theory. That's the cross product. It is simply a set of all ordered pairs where the first element A is in the first set A, and the second element in the ordered pair is from the second set B. Now I can have A cross A as well, and that would be denoted A squared, and that would simply be AA, or A is an A. But regardless, this is an ordered pair. It is not a typical set. It is a ordered set. Okay, it is the only ordered set that we talk about in this course. And you can introduce more variables. There could be a triplet here, as we talked about before, x, y, z, or k of them. Okay, which would be a k-tuple. Okay, these are ordered tuples. These things right here, that's the key. That's what we're after. An n-array relation on n sets is any subset of the Cartesian product of the n sets, the above example being a binary relation A cross B. So here, an n-array relation, a relation is, on sunsets, any subset of a Cartesian product. So that's what a relation is. Let me repeat that. This is the Cartesian product of two sets. This is a binary relation. Now, there could be a whole space of these ordered pairs based on all the possibilities of A cross B given A and given B, those two sets. But any subset of those ordered pairs is a Cartesian product, is a binary relation in this case. So once again, an n-array relation, here it's a tuple, is any subset of the Cartesian product, that's the Cartesian product, of the n sets. Okay. So also we have inverse relations. For R to be a binary relation, for set A to be, and let R be a binary relation from a set A to the set B, i.e. R is a subset, R is the relation, is a subset of A cross B. The inverse relation is simply by changing the ordered pair. Okay, so you just simply change the order. Instead of A, B, now it's B, A. That's an element of B cross A. That's the inverse, where AB is an element of R. Okay, so AB is an element of R. You reverse them for the inverse relation. So every pair AB and R, for every pair, the inverse relation contains the pair BA. The inverse flips the direction of the relation. That's all that's to it. So A is 1, 2, B is x, y, R is 1x, 2y, for example. It could be many more than this. It could be 1x, 1y, 2x, 2y. Those are the four possible ordered pairs that come from these two binary sets. But we picked a subset, which is these two, and its inverse is right here, simply by reversing the ordered pairs. Okay, so as you can see, we can go all the way up to n subsets. The Cartesian product of n sets, A cross A2, A1, A2, all the way to AN. A unary relation is only one participant, not A cross A, which is binary, but just one element A. R is a subset of S. That is a relation, okay? Unary relation, one participant, is a special case of a n-ary relation, R, on a set S, such that R, the relation, is a subset of S alone, one set. That's what unary means. As opposed to binary, we already talked about what binary is. Here's the most famous binary relation that you've heard about already, R2 space, okay, real space, R cross R. R cross R cross R would be 3 space. So Let A represent, these are examples of Cartesian products. Let A represent the set of all students at a university, and let B represent the set of all courses offered at the university. What is the Cartesian product A cross B, and how can it be used? So the Cartesian product A cross B consists of all the ordered pairs of the form AB, as by definition, where A is a student at the university, B is a course offered at the university. So one way to use the set A cross B is to represent all possible enrollments of students in courses at the university. So what is the Cartesian product of A, 1, 2, B, ABC? Well, it's 1A, 1B, 1C, 2A, 2B, 2C. That is the as a subset. The set itself is a subset, so there we have it all expressed out here. So it's the cardinality of A and the cardinality of B. You take those and multiply them. 2 times 3 is 6. So there's 6 elements, 1, 2, 3, 4, 5, 6. So you can see how that works. The cardinality I just described is simply the product rule, application of the product rule. Note the Cartesian product A cross B and B cross A are not equal unless A is the empty set or B is the empty set. So that A cross B is the empty set, or A equals B. So you can't, these things are not commutable, non-commuting. The Cartesian product, and hence the subsets of that, which are relations, are not commutable except in special cases. You can't switch A and B. We already said that because this is simply the inverse in what we just discussed here. All right. So examples of relations. So for example, R, a relation, could be A0, A1, A3, B1, B2, C0, C3. That's a relation from the set of A equals ABC to the set of 0, 1, 2, 3. It is simply a subset of all the possible sets, which is A0, A0, A1, A3. Okay, that's A0, A1, A2, A3, B0, B1, B2, B3, C1, 0, C1, C0, C1, C2, C3. That's all the possible elements of the Cartesian product. And this is simply a subset. This is a subset of all the possible ordered pairs of the Cartesian product of A cross B. So a relation from a set A to itself is called a relation on A. Okay. What is A cross B? Well, I just enumerated the whole thing for you. Okay. It's just every possible, here we go, A0, A1, A2, A3. Okay, you see how I did it before, and this is how you do it. Some properties of the Cartesian product. Well, for any set A cross the empty set is the empty set. Similarly, the empty set cross A is the empty set. Don't forget that. One needs to list all ordered pairs where A is an element of A and B is an element of B, and there are none here. There's none in the empty set. So it is simply the empty set. Does that make sense? Here are some identities. Connection of a Cartesian product and the binary operations of union and intersection. So, these binary are these ordered tuples or k-tuples are sets. They're ordered sets, ordered pairs, or ordered triplets. And they're related, of course, to set theory as follows. For any sets A, B, and C that's in a subset of the universe of discourse U, A cross B intersect C equals A cross B intersect A cross C. It's sort of a distributive property. And you can see it works for union as well. And then you can take A union B cross C and go the other way. A union B cross C is A cross C union or intersect B cross C. These are easy to prove. So here we have them, okay? And let us prove at least A. Let's prove A right now. So let me find my pen. So what do we have here? So proof of 5.1a. 5.1a. All right. Am I there? Yes. Okay. We'll only prove this one. The rest of them, B, C, and D, are left to the reader. We use the same concept of set equality. Okay. As in definition 3. Okay. Even though the elements here are ordered pair. As you've seen already, these are ordered pairs. They're still sets, and so we can, manipulate as in these. Let's just make sure we remember what we're doing. Okay, you can see here mixing the Cartesian product with our normal operations of intersection and union. So, okay. For any A, B, and U, in the universe of discourse, that's supposed to be a B element of the universe of discourse. AB, the ordered pair AB, is an element of A cross B, B union C, intersect C. Okay, that's kind of an element argument method, and B is an element of B intersect C. Okay. Oh my God. Okay, wait a minute. I've already screwed it up here. For any AB, an element of A is biconditional with, I forgot this part. A is an element of A. Okay, this goes to that. And B, intersect B, intersect C. B intersect C is logically equivalent to B. A is an A. Okay. And B is an element of B. C is in, okay, B is an element of B, and C is logically equivalent to A is an element of A, and B is an element little b. Little b is an element of C, and these conditions are logically equivalent to A, B, the ordered pair, is an element of A cross B, obviously. And the ordered pair AB is an element of A cross C, which is the direction we're headed, which is equivalent to AB, the ordered pair AB is an element of A cross B, union or intersect A cross C. So it's like the element argument method. So we've proved that we've proved the first one, that A cross B intersects C equals like a distributive property, and we did it more or less like with the element argument method. You can just go through that on your own if you want. There it is. Um, I'm copying from the notes, obviously, but it's easier if I write it out for you so that you can follow the logic rather than just listening to me read it off to you. That's why we do this in math. So, more properties of Cartesian products. So we've already mentioned that the product rule holds for cardinality. And so by the product rule, the cardinality of the Cartesian product is simply the product of the cardinalities of the individual sets. They're not commutative. We already established that. And it's not associative. A cross B cross C is not equal to A cross B cross C. The parentheses in logic always are right first. It goes to the right side of an equation first. We talked about this back in chapter 1. And so order is obviously important because these are ordered pairs, ordered k-tuples, ordered sets. Now, the one textbook, not Rosen, but Grimaldi uses script R. It doesn't matter. And we usually use this infix notation. A is a relation on B. And if it's not, then A is not a relation on B. That's the common infix notation. So A, B, and R is actually shorthanded as A, R, B, infix notations. If it's prefix, it's A, B, R. But we do this with infix. That should be straightforward. Representing relations with graphs. Okay, so this is the digraph thing I was talking about. So it's really simple. Let's just get to it. So there's 1, 1. That's a loop right there. This is node 1, node 2, and node 3. If you have the ordered pair 1, 1, then it's just a loop that comes back to itself. 1, 2, that's that one right there. 3, 2, that's that one right there. So that is the digraph of this relation right here. It only has 1, 2, 3. They're called edges. These are edges. These are called nodes, all right? Or vertices in graph theory. Generally vertices, nodes, but these are called edges, okay? So there's some special ones. The empty relation is simply the empty set. Full relation is the set X cross Y. That's the full relation that you just expand everything out. The identity relation on set X is the set XX, where X is an X. So it's just simply this binary relation. It's like X cross X. X cross itself, okay? The empty relation or void relation contains no ordered pairs at all. This means that no element of the set is related to any other element, not even to itself, okay? Also called universal relation on a set A is one in which every element is related to every other element, including itself. So, like for example, this is a full relation on these two, A and B. Okay. The identity relation on set A is one in which every element is related only to itself. It includes all pairs of the form AA. For example, A equals 1, 2, 3, R equals 1. The identity relation is 1, 1, 2, 2, 3, 3. Each element is related only to itself, not others. So that's the identity relation. Don't forget these three very basic, important relations. But look, there's all kinds of relations we're going to talk about here. So is the universal or full relation, the empty relation, identity. We've just done those. The rest of these here are the rest of this presentation. We will talk about, excuse me. Sorry about that. Almost every one of these, not complement of relation, but you can imagine what that is. The void relation, we're not going to talk about that, but you can see there's a lot. Classification. So informally, here we go. This is the stuff you really have to know. A reflexive relation is one such that each element is related to itself. So this relation right here is irreflexive. It is not fully reflexive. Okay, it means at least one loop exists in the thing. If it's completely reflexive, that means every node has a loop back to itself. So a reflexive relation is one such that each element is related to itself. So what I showed you here is actually known as an irreflexive relation. We'll define those later. A symmetric relation is one in which such that if any one element is related to any other element, then the second element is related to the first. It's like this, people. Just look at me. here's a node, here's a node. So there's an arc going to this one, or an edge, and one returning this way. And instead of drawing the two, we just draw a straight line without arrows. So a symmetric relation is simply one in which, here, I'll give you a really good example. Why not? So here's the digraph of a symmetric relation. So we have a point A, point B, point C. So there I've got one going this way, I got one going that way. I've got one going this way, I've got one going this way. I've got one going that way, I got one going this way. That's a symmetric relation. So for every edge, there's a complement, and that's all she wrote. Transitive. Okay, well, transitive, let me just, a picture says 1,000 words. Transitive is like this, where I have 3 nodes. Now, if this can go there and this can go there, then this can go there. You can complete the triad, okay? If you have this edge, you have that edge. Transitive relation means you can close the digraph. Transitive relation is one such that if any one element is related to a second element, and the second element is related to the third element, this first element related to the second element, second element related to the third element. So I drew it backwards here, but you get the idea. Okay, once again, if any one element is related to a second element and the second element is related to a third, then the first element is related to the third. So, I mean, I drew that kind of dumb. All right, let's do it again. So, if one element is related to that element and this element is related to another element, then this element, okay, A, B, C. So if you have A, B, and B, C, then you have AC. Okay, that's the formal way of stating it. Transitive relations are have a proviso, a caveat. Let's talk about it. Warning, this is an inadequate definition since the first and second elements need not all be distinct. How about that? Remember, we can have, the identity relation, which is XX or AA. So in that case, we have a proviso. So definition of reflexive relations, we have to provide a much better definition. The definitions we gave right here are too loose. Okay, this is just describing in natural language what these things are, but in reality, okay, a reflexive relation is as follows. Let A be a set and let R be a relation on the Cartesian product of A with itself. We say R is reflexive if for all A and AA is in R. So every node has a loop. Every node A for every A, okay, this is sort of weird. It should be like AI. Anyway, every node has a loop on it. For all A that's in A, the Cartesian product of AA is in R. So for every element, there's a loop. In other words, every element is related to itself. The equality relation, let A be 1, 2, 3. Define R as 1, 1, 2, 2, 3, 3. Okay. Here R is reflexive because each element of A appears paired with itself. Okay. So that's definitely reflexive. Okay. Symmetric relation, let A be a set on the Cartesian product of A with itself, that binary relation. We say R is symmetric if for all A, B, and A, the ordered pair AB being an R implies the ordered pair BA is also an R. So, this and this. Okay. Example, friendship relation. Alice, Bob, and Charlie is set A. There's a relation Alice, Bob, Bob, Alice, Alice, Charlie, Charlie, Alice. If Alice is friends with Bob and Bob is friends with Alice, then Alice is friends with Charlie. Charlie is friends with Alice, thus R is symmetric. Okay, it's a cute demonstration. Then there's a thing called antisymmetric. My goodness, we're getting lost here. I've got a summary slide which will put it all together. A relation R on a set A is antisymmetric. I had my own notes that were very messy, and I decided to clean them up for this class. And I used ChatGPT to take my notes and then make them look neater. As you can see, if you see this right there, you know it's ChatGPT. And it does this. It has these, these spaces here, these things you have to correct for. So you can tell when somebody's giving you ChatGPT with math for things like this. But these are based on my notes, and I just wanted it to give the same clean appearance to all of these. And that's a real good editing tool. ChatGPT is an excellent editing tool. But you got to look and see what it's doing. It makes mistakes all the time. Okay, an antisymmetric relation. A relation R on a set A is antisymmetric if for all A and B that are elements of A, AB is in R and BA is in R implies A equals B. In other words, the only way two distinct elements are equal can relate both. The only way two distinct elements, A not equal to B, can relate both ways as if they are actually the same element, okay? Then it is not possible for A and B and BA to be in R, okay? So example, the less than or equal to relation, okay? Let A be 1, 2, 3. Define the relation as A, B as the Cartesian product, elements of the Cartesian product, A cross A with the constraint A is less than or equal to B. So in pairs, we have 1, 1, 1, 2, 1, 3, 2, 2, 2, 3, 3, 3. Obviously, that satisfies that constraint. Check antisymmetry. Well, if 1, 2 is an R, 2, 1 is not an R, so we're okay. If 2, 2 is an R, 2, 2 is in R, same element allowed. So notice the antisymmetric is not the same as symmetric. Antisymmetric is not the same as not symmetric. That's what I meant to say. Antisymmetric is not the same as not symmetric. The terminology is really weird. Transitive relation, a relation R on a set A is transitive if for all three A, B, and C being an A, AB is an R and BC is an R implies AC. AC is in R. So example, the less than or equal to is transitive as well. So if R is AB on this A set A, which is 1, 2, 3, then 1 is less than 2. This is on this set right here. 1 is less than 2 and 2 is less than 3 implies 1 is less than 3, obviously. 2 is less than 2 and 2 is less than 3 implies 2 is less than or equal to 3. So sure enough, yes, it's transitive. This is a relation. Okay. So here's the summary that you won't find anywhere else except in my notes. Nobody seems to work on this to satisfy the confusion. They just throw these words at you, and you're never sure if irreflexive means not reflexive. So I just give it to you straight here. It's reflexive, for example, if every node has a loop. It's not reflexive if there exists AB and AA is not in R, meaning it's not reflexive, it has no loops. Anti-reflexive, well, that is if and if A is an A and the ordered pair AA is not in the relation. So not reflexive means there exists an A such that A and A is not in R. So it just means somewhere in there, the loop here with a reflexive relation, every node has a loop back to itself. The not reflexive means there can exist nodes that don't reflect or loop back to themselves, whereas it doesn't mean the rest of them don't. So if there's just one missing loop, then that's called not reflexive. Reflexive has to be loops on every node. Anti-reflexive, on the other hand, is a special kind of relationship that for all A, anti-reflexive means nothing's in there. There are no ordered pairs. So not reflexive, anti-reflexive, that's very confusing to most people. It was to me when I first learned it. A symmetric relation, is obvious. A, B is an A. A, B are in the set A, then A, B are ordered pairs, and the relation implies BA is also in R. So again, we have these complementary arcs from two nodes. Not symmetric means there exists an ordered pair such that there exists set A, B in A, such that the ordered pair A, B is in R, and B, A, the ordered pair somewhere in there exists, right, is not in R. So it's very much like not reflexive. It's just that you can have most of them having complementary pairs, it works, but just one may not be there, so that's not symmetric. Antisymmetric means there are no loops, or there are no complementary pairs at all. So it's for all AB, that means everything, not there exists, okay? AB is in R and A not equal to B means BA is not an R. So we don't have that complementary arc at all, ever. Okay, antisymmetric. Transitive, it's pretty obvious. A, B, and BC are an R implies AC is an R. Not transitive or intransitive, some people call it. Oh, not symmetric is called asymmetric. Not reflexive is called irreflexive. I mean, you've got to watch out for the wording that people use. These not reflexive, irreflexive are commonly used in place of each other in different textbooks. Symmetric, not symmetric, and asymmetric. This notation I have is much more straightforward. Using asymmetric, I think, is dumb. Using intransitive, I think, is dumb as well. All right. So not transitive means that there are cases where A, B, and BC do not have a third AC. Okay. And antitransitive means there is in no place that transitive relation. Okay, so remember this. I think that's very, very good material for you to remember. So remember this dough, this stuff here is a little more complicated for symmetry. Okay, next slide. Symmetric and asymmetric and antisymmetric are all universal definitions. A binary relation R on a set X is symmetric when for all A, B, all right, you have A as a relation on B implies B is a relation on A. Okay, that's symmetric. An example is married to. A binary relation R on X is asymmetric if for all A and B in X, AB implies there is no BA. Okay, that's asymmetric, as we talked about here. It means there at least exists one that doesn't relate back. And a binary relation R on X is antisymmetric if there is no pair of distinct elements, such that AB and AB, are indistinct. They have to be the same. So remember that. Remember these definitions. All I'm doing with those is summarizing what most books say. Okay. Just concentrate on this, and notice that the one in red here is well, it's the same as this. I should just take that out. So draw the directed graph that represents the relation AA, AB, BC, C. Oh, this is so simple. All right. So let me just do it. So you got A, B, C, and D. A, B, C, and D. And I have to look on the screen here, unfortunately, but I'll just draw it for you. Okay, so it's AA. This is A, B, C, D. Okay, AA is a loop. AB. Okay. BC, BC. CB, CB. Oh, that's at least partly symmetric. CB, CD, CD, there we go. DA and DB, DB. All right, so that's what I get. It looks something like this. So there's AA, AB, BC, CB, CD, DA, and DB. All right, that's the way it is. What about the rest of these? Well, if you were in class, I'd have you do these on your own. So, and these list the ordered pairs in the relationship. Well, here clearly it's A, C, C, B, B, C, and A, B. I mean, come on, these are obvious. Here, this one is is AA, BB, CC, AC, BA, and BC. So this is reflexive and it is transitive. Reflexive and transitive for sure. Okay, so here we list all the pairs, and it's just the way I did it. AA, AC, BA, BB, BC, CC, just like I said for the first one. Second one, same thing, AA, BB, CC. And then the other ones, AA, wait a minute, okay, 24. There is AA, AC, BA, BB, BC, CC. So each node has a loop. You can figure out the rest on your own. Here's a symmetric, fully symmetric relation right here. You can tell just by looking at it. Right. So let's talk about graphs. Okay, these are very important. Now this is just a blurred version of this. So when we talk about closure, let me just talk about something. Oh, I wrote on this paper. What a fool. Closure. Closure means that addition is closed under integers are closed under addition. So for an integer a in the set of integers and b is an element of the set of integers, then a plus b is a set in the set of integers. That's addition is closed. If I put for all, that would be more proper. And for all of these actions, they're in Z. So closed means it's in there. Irrational numbers are not closed under addition. We talked about that before. So a plus square root of 2 and a minus square root of 2 are both irrational numbers, but when I add them together, I bounce out of irrational numbers and I get 2a because these cancel each other off. So that is not closed under addition. Now, here we actually have the ideas of closure relating to these digraphs as well. So this is some given relation. So it's, there's no A, B, C's, or D's, so we just have to look at it. So if each there's a lonely node there, that is a possible graph. But all the nodes have loops. That's called reflexive closure. Here, this is symmetric closure. If you look at the definition, transitive, obviously, transitive, it could still have the odd loop, so it's irreflexive. Not reflexive, I should say, but not anti-reflexive. So it's reflexive. It's irreflexive. Oh God, I'm sorry. Because not all nodes have the loop, but it satisfies the transitive property. I got a loop going from here to here. I got a loop going from here to here. Therefore, I have a loop going from here to here. Okay, so this is transitive closure where you have everything is reflexive. Symmetric closure means that this is not only closed under reflexivity, but under symmetry as well. And that's because we have these double-headed arrows, okay? The double-headed arrows mean, I have an arc going this way and an arc coming back, or an edge, I should say. There's reflexive closure and transitive closure, because each node obeys the transitive property. And symmetric transitive closure and reflexive symmetric transitive closure. This here satisfies all of them. This is called an equivalence relation. We'll get to that later. If it's reflexive, symmetric, and transitive, which this clearly is. So memorize these graphs. Or should I say, understand these graphs, okay? Understand them, study them well. This is just one good way of describing all the possible kinds of digraphs that appear with relations. By definition, for it not to be transitive, A and B and C are in R while AC is not, okay? So that's not transitive. Here, all pairs of pairs A, B, and BC are in R, okay? And we have 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 2, 1, 1, and 1, 3, 1, 2, and 2, 2, 2, 2, and 2, 3, 2, 2. So this is definitely reflexive. And so let us see if the arc AC, okay, if we have A and B, AC, now we're looking for AC, for God's sake, We've got AB and BC. Let's look now for AC. And we run through this, yes, 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 all the way through. It satisfies these pairs. So 1 to 1, you get a loop. 1 1 to 1 2, that means you get 1 2. And 1 1 to 1 3 means you get a 1 3. Okay, you get it? So yes. Therefore, it is reflexive and transitive. You see how you do that stuff? Consider the relation R on the set A, which is 1 2 3 4, defined by 1 1 2 3 2 4 3 3 3 4. So what do we have? It's not reflexive because there's no 2 2. Since 2 2 is not an R and 1 1 is an R, the reflection is neither reflexive nor irreflexive. So it is not reflexive because it has loops. Okay, it's not reflexive. See, here's that. It's the terrible use of the words. Okay, when we defined it, let's go back to our definitions. So, irreflexive means not reflexive. Whereas so don't forget that these two are interchanged, and that's exactly what this individual is doing right here. Okay. This one right here, I'm sorry. Okay. Since we don't have loops on everything, it is not reflexive. Or says it's not reflexive, nor, I think he means not reflexive here, which is, see where the confusion comes from? It is definitely not reflexive, okay? According to my definitions, go by my definitions in this course. Go by my definitions so there's no confusion, all right? Just remember that these things are used interchangeably. Irreflexive should mean not reflexive, okay? And sure enough, it's true because, come on, it's got two nodes that have loops while the node 2 does not. So it is not reflexive, but it is not anti-reflexive. Anti-reflexive would mean it's got no loops at all. We have 2, 3 in R, but 3, 2 is not an R, so it's not symmetric. For any A not equal to B, only one of 4 possibilities, A, B is not an R, BA is not an R, and AB is an R, or BA is an R can occur. So R is anti-symmetric. Remember the possibility that A equals B when they can't equal each other, the third element. By going through all the ordered pairs in R, we verify that when AB is an R and BC is an R, we have AC, so it shows that R is transitive. Therefore, R is anti-symmetric and transitive. All right. We talk about a fully transitive, but since we have loops here, you could say it is not reflexive as well. So this is an incomplete description, but that's how people in this area talk about things, and they're inconsistent with each other. So like this textbook that you have is inconsistent with the other textbook that we use with this terminology. My terminology is the best terminology. This is the terminology that you should stick to. There is no confusion at all if you use these words properly. For example, reflexive means every loop exists. Not reflexive means there may be a missing loop, but they still can all have loops. But if no loops are there, it is anti-reflexive. If no symmetric pairs exist, it is anti-symmetric. If no transitive relations exist, it is anti-transitive, okay? Anti is not the same as not. Not transitive simply means it's in between transitive and anti-transitive. That's the best way of looking at those words. But your book uses this note here, uses irreflexive properly. It uses irreflexive properly. Irreflexive. So it's not reflexive nor... See, he uses it wrongly. Here he's saying not reflexive. It is irreflexive according to my definition. All right, after that. So the relation T on R star is defined as A is a relation on B, logically equivalent to A over B is in the set of rational numbers. So A over A equals 1, which is it's in the set of rational numbers. The relation T is reflexive. It follows that T is not irreflexive. The relation T is symmetric, but A over B can be written as M over N for some integers M and N. So then a reciprocal is B over A because B over A equals N over M. So it is symmetric. Since root 2 relation T on root 18 and root 18 relation T on root 2, okay, since those two yet root 2 is not equal to root 18. We conclude T is not antisymmetric by the definition of antisymmetric. If A over B and B over C is in Q, then A over B equals M over N and B over C equals P over Q for some non-zero integers M and PQ. Then A over C equals A over B times B over C equals MP over NQ. Hence T is transitive, okay? So this relation is reflexive, symmetric, and transitive. That is an equivalence relation. That is an equivalence relation, as we'll see shortly. The relation U on the set of integers is defined as 5 divides A plus B. Well, the relation U is not reflexive because 5 does not divide 1 plus 1, okay? It is not irreflexive either because 5 does not divide 10 plus 10, okay? So in other words, in my definition, it is irreflexive. They say it's not reflexive. They mean anti-reflexive. It is not anti-reflexive. 5 divides A plus B is obvious because because A plus B equals B plus C. It's you can see how these things work, how you can identify. We claim U is not antisymmetric. For example, B divides 2 plus 3 and 5 divides 3 plus 2, yet 2 is not equal to 3, so it is not antisymmetric. It is not transitive either. You can figure that out right here. It's pretty obvious. So the relation U is simply symmetric. These are nice exercises. Again, you have to watch out for the terminology. It's nice if it's consistent, but I have to expose you to the real world. That's why I choose these so that you can look at the terminology I have here and understand why I've chosen this terminology so there's no confusion. Okay, once again, reflexive, not reflexive, anti-reflexive. It's not reflexive in between reflexive and anti-reflexive. They could be, there exists a loop there. Not symmetric, there could be a pair. Not transitive, there could be an arc, okay, connecting 2 points. AB, BC, AC. Okay, there could be one there. Important note regarding transitivity. Now pay close attention. This is one of these vacuous arguments. Vacuosity, okay. Any relation which contains only one ordered pair is vacuously transitive. That is, there are no counterexamples. Transitivity requires a counterexample, okay? And the relations that violate transitivity. So a relation R is transitive if, here we go, X, Y is an R and Y, Z is an R, implies X, Z is an R. This is a conditional statement. Vacuousness here requires the hypothesis above to never be true, okay? This can never be true. Consider A going to B. To test transitivity, we require the structure X to Y, Y to Z. So we could check if X goes to Z, but in our diagram, there is no arrow leaving B in this example that we have here. So we cannot form a two-step chain. Why is it vacuously transitive? Since there is no two-step path, there is no situation where transitivity could fail. So this is a very subtle argument. The absence of a counterexample is why this relation is vacuously transitive. That you must understand. This is a very subtle point. Okay, I thought there was another slide to go along with that. There isn't. I think this argument makes it clear. Just go through it again. This conditional statement here. Okay, that's the conditional statement. A implies B. It's vacuous if you look at the fact that, like, for example, 0 equals 1 implies 1 equals 1. 0 equals 1 is always false, so it's vacuously true. So vacuousness here requires the hypothesis, this right here, to be never true, to be always false. Well, this is always false if we consider A to B, okay, just A to B by themselves. Okay, so any relation which contains only one ordered pair is vacuously transitive. So here it is, A to B. So we need X to Y and Y to Z, but there is nothing coming out of B. That makes it, we can't form the two-step chain, so we can't disprove transitivity, so it's vacuously transitive. I hope I made that clear. Cardinality. Okay, well, we already talked about this. The cardinality of relations. Uh, well, we found out earlier the cardinality of the Cartesian product. Um, sorry. Yes, the cardinality of the Cartesian product is 2 raised to the um, cardinality of the set. So it's 2 to the 6. 2 to the 6 power. We got this from the power set. The power set is the number of subsets of any set. The number of subsets is the power set, and you remember it was a exponential number 2 to the cardinality of the set. Okay, and so that's where this comes from chapter 1. How many binary relations are there on a set with n elements? Well, a relation on a set S is a subset of A cross A. Here, with n elements, it's just a set. Binary, though, that means it has to be A cross A. Because A cross A has n squared elements, when A has n elements and a set with m elements has 2 to the m subsets, then there are 2 to the n squared subsets of A cross A. Thus, there are 2 to the n squared relations on a set with n elements. For example, there are 2 to the 3 squared equals 2 to the 9th equals 512 relations on the set ABC. All right. Mm-hmm.